Okay, also I'm going to share my screen. Can y'all see? Okay, Elum says yes. Thank y'all. Thank y'all. Okay, wonderful. Well, one last chance. If anybody has something specific that they want me to talk about, or if they have questions, now is the time. Okay. Well, if you decide that you have questions, our wonderful PT Glory is here, so you can send her a DM and she'll help you out. If you have questions about what I'm talking about, unmute yourself and interrupt me. I will not be butthurt, I promise. Okay, so the first topic today is the Enum class, which if y'all went to your lab section, you would have seen like a few slides on Enums, and like always, I still don't believe that seeing code on a slideshow is ever going to like actually be enough to help you learn. So I've actually coded some stuff so that y'all can see what it looks like. So I made this example file right here called enum.cpp, and essentially this is what it looks like to define an enum class. It's not scary. It's basically like any other object that you have in C++, right? So you declare enum, this keyword right here, you give it a name, and then you open brackets, and very similar to the way that you would declare an array in C++, you just delimit your entries here by commas. As you can see, my text editor recognizes that these are enums, so it changes the color to blue. And we've got two enums here. The point that I wanted to make between the two of these is that when you declare an enum, and you don't specify the values of the enum, the compiler will assign these automatic values. So as we'll see in a second, this will be this text right here, red, it's going to be mapped to 0, orange is going to be mapped to 1, and so on and so forth. If you can see, if I can highlight over it, it'll actually say, like you can see enum and then color, and then the 2 colons. Remember, the 2 colons are the scoping operator. So within the enum scope that is color, violet is equal to 6. And then if I hover over these, you can see you can set these explicitly. So you might have cat, dog, and then mouse is 10 in this example. So in the main function here, I just declare color, my color, and then color orange, again using the scoping operator, and then I print out that color. So should be what orange is 1, so it should print out 1. And then I made an animal, mouse, which I think this should print out 10. So if we go ahead and open up this in a terminal, let's go ahead and run our compile file. Okay, and ./data-out should run the executable. And as you can see, my color is 1 and my animal is 10. Let's change this up. Let's see, green maybe, dog, and then see what that gives us. And then as you can see, yeah, so green is 3 and dog is 2. So why would you use an enum? Well, basically, if you want to have a list of options, like maybe you'll see this in a switch statement or an if statement, and you want them to evaluate to numerical values for the sake of simplicity, right? It's easy to work with 1, option 2, option 3, and so on and so forth, but you still want to actually explicitly say what these options represent. Enum class is a good option for you. So these are the 2 different ways you can declare an enum. It's not scary, I promise. When you see it on the next PAs, y'all will all be prepared. So that's enums. Any questions? I think it's pretty simple. Cool. Okay, I'm just saying nobody taught me enums when I took this class. And when I saw it the first time, I was like, what is going on? Because nobody warns me. Okay. So the next topic we're going to cover is we're going to do some practice over runtime analysis. This doc was linked under week 3 topics, so I'm just going to briefly look through some of these examples. This is one of the legendary TAs from the past, Dante. This guy's like mythical level name, so this is good stuff right here. Essentially, what I want to cover is like specifically like the minute details of how runtime is calculated within this class. So if y'all have taken other classes, they might have different specifics for how they want to count runtime. And we're going to kind of be touching over that and like how you can tell what is a good answer, what's a bad answer. So specifically for this class, some things I want to point out. Obviously the intro to this document here is making the point that you can represent for loops or any type of iterative process with this summation character right here, which y'all have seen that before. Some important remarks. I would say number one, when you're counting runtime operations, you don't count what happens. You don't count the loop handling operations. So like this allocation right here, so I is equal to 0, I is less than n, this is a comparison, and this increment, none of those count to your runtime. So when you're deciding your runtime, you basically ignore this line and you're only looking at what actually happens inside the function. And in a similar fashion, the return statement for a function also doesn't count. So this right here, return total, does not actually affect your ultimate runtime. So that being said, one other thing to note is that when you see this syntax right here, where you've got a summation character and you start at A and you end at B, this actually evaluates to B minus A plus 1. And, in this example, the sum is 1. So it's going to be, this times whatever is going to be. And you'll see that. Y'all are going to see that in a second. But essentially, you can imagine like, if you had an example like imagine A was 1 and B was 4, you're going to have 1, 2, 3, 4, so 1 plus 1 plus 1 plus 1. So B is going to be 4 minus 1 plus 1 is equal to 4. The sum from 1 to 4 of 1 is it works out. If you don't believe me, try it yourself. This formula actually does work. And we're going to see that be useful. We're going to see that formula be useful right here. So not to scare y'all, because this is like definitely like advanced level stuff. You'd probably like see this in 4.11, I would imagine. But okay, anyways, another point to make is that runtime, when we're talking about time complexity, so big O notation, we might theoretically be missing large constants, like large constant multiples. Like for instance, if we have a function that is 1,000,000 n, it's still linear, but we've got a huge coefficient in front of it nonetheless. And that's something that you actually don't ignore when you're calculating runtime. So for this example, we've got random array. We're performing a few different functions. So the two functions in this example that would count towards runtime is we've got an access. So array, and then we're accessing it, and an access counts as +1 on the runtime. And then also we've got some kind of function here called rand, and we don't know what happens under the hood, but in the documentation, I think it says that random is linear. No, it's constant time. Yeah, so it's constant time. So you've got an array access, which is constant time, and you've got a random function, which is constant time, and you've got this modulo operation, which is constant time. And those are represented by this one right here is the array access, and then this is the modulo, and then this is the random. And even though you're doing all this work, like you might have a super scary random function that might, take 1,000,000 seconds to calculate one random number, it's still technically constant time. So that's the point from example 2. For example 3, y'all have seen this before. If you were at the last Sunday review, you would have seen this algorithm is. Does anybody want to speak up and take a guess as to what algorithm this is? I know y'all are, you would rather just watch. Somebody who's brave enough to speak up. Maybe in the chat, somebody. Oh, we got someone. Yeah, selection, correct. Good work, y'all. So as you can see, what's happening here in this example is we are iterating from 1 to, and I actually don't like the way that this guy did this notation right here. I think that's kind of a, yeah. I think that's kind of a low class way to say that you're stopping at n-1. But okay, anyways, basically what's happening is you're starting at I is equal to 0. You're stopping when I is less than n-1, incrementing I. So that's the outer shell of the for loop. And then each time within that for loop, you're finding a minimum, updating the minimum if you find a new minimum. And then these three lines perform a swap for, you know, each minimum to be in the correct place. So this is selection sort. Indeed, thank you all for those who answered in the chat. That is correct. So this right here, I don't know why it's off center, but this right here basically is the runtime for this implementation of selection sort. And we can kind of break it down piece by piece. So essentially we're stopping at n-2 because as you can see right here, we're starting at I is equal to 0, and we're ending when n is equal to n-1. And then you just add 1 here for and that like why you have to add 1, like why this +1 exists. Like if you don't take my word that it needs to be there, just read through this document, and Dante explains it quite well. But essentially this sum represents the outer for loop. This +1 right here, I think, is the allocation for size t min is equal to I. So that's where you get the +1. This for loop right here, starting at j is equal to I plus 1 and then ending 1 before n-1 should be the balance for this inner for loop. Yeah, so j is equal to I plus 1, j is less than n, and then, you know, as I said before in the previous example, you've got to stop 1 early. And then let's see, so for each iteration of finding the minimum, it's 2 operations. So those 2 operations are going to be this comparison, and then this minimum is equal to j, and then the +3, which actually exists outside of this summation. So there should be parentheses from here to here basically. The +3 is these 3 operations, these that are happening there. And I don't want to bore you specifically from how you get from here to here. You know, obviously it was going to be an n² time complexity, so it's, you know, not surprising that this is the answer. But essentially you can just apply the formula that I showed you before. So b minus a plus 1 times whatever was in the actual runtime. So in this case, it's 1. So as you can see, b minus a plus 1 times what the runtime was, and that's the way that you can break apart the summation. And then once you do algebra, you get down to here, and that like is basically everything, you know, all wrapped up, and then some more algebra. Essentially, what he's doing here is he's splitting this summation into 2 different summations, which is a property of summations that you can do. Like he splits the I to its own summation, and then he has n+1 on this summation, and then he evaluates 1 at a time, b minus a plus 1, and then he simplifies here, and then b minus a plus 1, and then there you go. So sorry to go through, like, this is so scary. That's so scary. That's so much math. But I mean, hopefully that'll give you all like maybe some pointers for how you would evaluate a runtime, because this is one of Dr. Lake's favorite style of question. Like this will be on every exam. I wouldn't be just telling y'all about this stuff because I'm interested in it. Like it's very important. Example 4, binary search. Y'all have seen a similar example. So let me pull it up actually. So the example of binary search that I showed y'all last week in review was the iterative example. So this is binary search using a loop. So essentially you've got a left and a right pointer, and then this is the case that terminates the loop, and then you iterate and you handle it. But this implementation of binary search is recursive. I remember last week in review, someone had a question as to whether or not this is possible. It is in fact possible. I don't think y'all have gotten to recursion yet, so I'm going to skip this example. But if you're curious about what a recursive binary search looks like, it's this. See, example 5 is just array output. And, you know, it's again pretty similar stuff. Like you've got this O of 1 for whatever this extraction operator is, and then, you know, I'll leave y'all to this, but just wanted to brush up on big O. I think it's super important, especially if you want to pass the tests that Lake likes to give. Okay, let's see, what's next? Okay, by the way, any questions so far from the what we've covered so far? Anyone curious about anything? see. Anyone in chat? Okay, well, I assume that got it. I mean, I'm not.
All right. Can I add something?
Yes, please.
So can you help me to break down operation by operation how to count the big O again? So
Yeah, of course. Is there one of these
yeah,
examples that you would like to see, or
yeah. It's one of the example will be good.
do you like? I'm asking, do you have like one that you'd specifically want to see?
Let's try the sum one. Yeah.
This one? Okay. Yeah. So the runtime here is going to be 1 plus 2 times I is equal to 0, n minus 1, 1. So this is the runtime that we're shooting for. Well, actually, it's here. So this is the runtime that we're trying to calculate, and this is the correct answer based on this code. So as you can see, the things that count for runtime would be like this one right here is an assignment. So anytime you have something in memory and you're setting it equal to something else, that counts towards your runtime. So specifically in this case,
All right.
we've got long total is equal to 0. And because you're doing this assignment here, that represents the +1. And then for this for loop here, we've got unsigned int I is equal to 0, I is less than n. So this will actually stop when I is equal to n minus 1. Hence you have n minus 1 as the bound here. In for loops, we're used to seeing when we have less than something, we're used to like stopping one before that. So like when I see this, my brain goes like, okay, well, obviously we're stopping until we're just about to reach n, right? That's what y'all are used to. But specifically when it comes to summation notation, this thing up here on the top is its own case. So it actually will
All
be
right.
evaluated. So you'll be evaluating I equals 0, and you actually will be plugging in n is equal to 1. So it's just like different math notation between like computer science and math. Like I wish people could agree, but so essentially the bounds of this for loop right here are represented as the bounds of this summation. So I starts at 0, and then the last case that'll be evaluated is n minus 1. And then within the actual inside of this for loop, you've got a 2, which you might think like, why are you counting 2 operations for this one line? Well, I think that's covered right here. So this note, the plus equals is an assignment and an arithmetic operation, so it counts as 2. So
All right. Got it.
assume yes.
All right. So I already got it. So I mean, do we have one form of this to download after the review?
Oh, yes. So this I can here. I think this is on the canvas. I can paste this in the chat, and y'all let me know if y'all can see this. I hope that works. If you can't see it from there, I can like email you.
Oh yeah, yeah. All right. Okay.
Cool.
All right. Got it. Thank you so much.
Cool. Do you want me to go over another example, or is that
Yeah. Let's do one more example so I can make sure that I
yeah, of
understand.
course, of course. So this is kind of let's do 5 that we skipped. Okay, so this one right here is array output. So in this case, it says printing things. Yeah, so I think we're ignoring all of the times where I mean, no, we're actually counting all of the times that we're using this operator. So I don't know if y'all remember this operator from 121. This one is called the insertion. I think when you have a stream object, you don't like append or plus or anything. You actually use this operator. So as you can see in this example, we do in fact have a stream object. So we've got a std o stream, and then we're going to be moving stuff into that o stream. So that's not the point of this question. So don't freak out. That's too high level. But essentially for this problem, we're going to be counting how many times we do this operation. So obviously right away when we call the function, we do it once. So this is going to count as 1, which is represented by this +1 right here. And then at the end, you can see we've got return OS, and then we insert again. So the return statement itself actually doesn't count as an operation. So we're not counting the return as the +1. We're counting the insertion as the +1 because there's like technically there's another insertion that's being done on this line. So you +1 here, you +1 here. And then as far as what's actually happening on the inside of this for loop, the bounds from this summation correspond to the bounds from this for loop. So I starts at 0, and then the last case that we'll evaluate is when I is equal to n-1. So when I starts at 0, and then when I is equal to n-1. Inside the actual for loop, the first operation that we've got is OS insert array of I, whatever that is. So that would be 1. And then we've got this OS insertion right here, and I think the way that the lab slides said to evaluate conditional assignments was to just assume that they're always true, which is not what's happening here. So apology for the inconsistency. The lab slides, which I think is what y'all should go with, said like, if you have a conditional statement, just assume that it's always true, because for runtime and time complexity, you should be trying to calculate the worst case. But specifically what is happening in this example is they're waiting until this will trigger on the last case. So when I +1 is not equal to this is the last case, which is where they get the -1 from, I think. Yeah.
Oh, okay.
Yeah, because when I +1 is equal to n, that will be this, which is the ending of the for loop. So it won't happen. So essentially what they're saying is that for each iteration of the loop, you've got this one, which is this one right here. You've got this insertion, which is this right here. And then you're subtracting one because this conditional will get skipped on the last iteration, if that makes sense.
Oh,
And then,
got it.
yeah, that's kind of tricky. I mean, personally, if this was my problem that I designed for the exam, I don't think I would go into that much detail, but that's just like, that's I guess a discretionary thing. And then, you can see basically, and again, I don't like where this parenthesis is here because it kind of makes it unclear that this one should actually be outside, but anyways, basically there's just some arithmetic that's happening here now. So you've got the ones on the outside, those will be summed eventually. But you can actually pull the two, you can factor it out of the summation. So you factor the 2 out here. And then it's the formula from earlier, I think, something like that. You've got B minus A plus 1 somehow in there. I'm not exactly sure how you get from this step to this step, but it eventually results to 2n plus 1. So maybe y'all want to dig through this arithmetic here. But I hope that answers your example, and thank you for asking to clarify, because I'm kind of in touch with what y'all need to know, and what like how to fill in the gaps between the lecture, but I'm not always 100% sure. So
Yeah.
yes, thank you very much. Hope that sorts it out a little bit. And this code you can find, it's also linked under week 3. So if you want to try running these functions and seeing what they like actually look like inside an editor, and that's an option that you'll have to. So yeah, cool.
Okay, got it. Thank you so much.
Yeah, of course. Okay, so next topic is non-comparison based sorting. So non-comparison based sorting allows you to bypass the lower bound theorem, essentially. I think y'all have seen so far that the lower bound theorem essentially states that using a comparison-based sorting algorithm, you can get no faster than n log n in worst case. So the way that you get around that lower bound theorem is you actually don't do comparisons. And if you're not comparing elements to each other, there are some like little tricks that you can do to actually sort way faster. So the first of those that we're going to be looking at is, first that we're going to be looking at is called bucket sort, which the name of it pretty much gives it away. Essentially, you pick discrete like bins. Like if y'all have ever heard of like, discrete versus continuous variables, essentially you've just got like numbers on some kind of number line, and then you just arbitrarily pick like this segment will go in this bin, this segment will go in this bin, this segment will go in this bin. Essentially, so all you do is you iterate through however many numbers you have, and then based on where which bucket this number belongs to, you just put it in that bucket. And so see there's some animations here. And this is technically an O of N algorithm, because for each, you just have to traverse this list once, and then all of these buckets are in order. So you just basically put things in the buckets, and then you traverse through the list of buckets, and that's technically O of N. I think, I don't know if it said in the slide before, it could be O of N squared in the worst case. So best case is O of N, that's assuming that every number goes into one bucket, and then all of the buckets are just already sorted. So that would be O of N. If you add to these buckets out of order because of like the order of your input array. So for instance, like there's an example here, right? So imagine you add 34 to this bucket, but then later you add 32. You would have to call some kind of sorting algorithm on each bucket. So now it's N squared. That's in practice, this is still a very efficient method of sorting numbers. The sorting method that you would call on these numbers would usually be an insertion sort. I think on the slides, it's like, why would you, whoever designed it, whatever TA is confused about this. The reason you would pick insertion sort is because out of like the noob sorts, that being bubble sort, selection sort, insertion is almost always the most efficient. So there's that. And as some like trivia for y'all, if y'all have ever used Python and called the like dot sort in Python, it's actually kind of something kind of similar to the way that this works, but not to scare you off. Okay, so counting sort. This is the most important one from today. So counting sort basically utilizes auxiliary space, and it kind of makes a trade-off between extra space and runtime. So it runs very quickly, but it does require you to have a lot of extra space. It runs of O of N plus K, where N is the number of elements and K is the range of the elements. So y'all will see this in the example. So specifically, the drawback for counting sort is space complexity, which is probably worse than the previous slide made it out to be, because for counting sort, you need to have an array of the length equal to every possible enumeration of whatever you're trying to sort. So if you're sorting digits, you need to be working with arrays that have space for 0 through 9. If you're sorting like a range of numbers, like if you're sorting like you had like 1 through 20, now your array needs to be 1 through 20. If you're sorting characters, that being like 1 through 26, now you've got to have an array 1 through 26. And then if you're sorting numbers like 1 to 1,000, now you've got to have space for 1 through 1,000. So that'll become clear as I kind of explain what happens. So counting sort happens in 3 different arrays. So there's the original array, there's the auxiliary array, and then there's the sorted array. And y'all see this working. Essentially, the first step is to define the range of all possible elements within the array. So, right, like in this case, we have digits from 0 to 8. So 0 being one extreme, that being the left extreme of the range, and 8 being the right extreme of the range. As you can see, we've got that entire range, every single possible option within that range represented as a space within this array, and we initialize everything to 0. The first step is that we actually count how many of each discrete element we have per category, and that's why we need to have enough space for every possible category, because we're counting the number of occurrences of every possible category. So essentially, we have in the original array, we have 2 8s. So the 8th index in this array will, read 2, representing the 2 8s. We have, we have 1 0, we've got 2 2s, got 1 3, and we've got 1 5. And there will just be zeros left over where there's not elements. So I said that this process takes 3 arrays. So you've got the original array. The first step is computing the count array, and then the last step will be the sorted array. So what you're looking at here is actually, this is the first of the 2 auxiliary arrays. So you're given an array, and then you have to make 2 additional arrays. This one that you're looking at right here is the first of the helper arrays. So this This is the first of the auxiliary space. And then once you've computed the sums, you do a rolling sum across this array where, let's see, there will be an example on the slides. So yeah, so essentially what you're going to do is you're going to end up with something like this. So you're going to have a monotonic, that means it's like increasing or decreasing in one direction. So it's monotonic increasing array that tells you information about where each of these discrete variables might show up. So if you're confused, if I've lost you, that's probably most of you. I'm going to back up. So what's happening at this step? So y'all understand, you're given the original array, you count the discrete elements. To perform a rolling sum, you start with this element in the array, and then you basically make it so that each element succeeding it must be equal to or greater than the previous element. So it's a 1 here, and then oops, man, I'm so sorry. So it's a 1 here, you perform the rolling sum on this element. So 1 here, perform it on this element. It's a 3. Now this is going to be a 4. This is going to be a 4. This is going to be a 5. This is going to be a 5. This is going to be a 5, and this is going to be a 7. So as y'all can see, at each iteration of this rolling sum, basically we're just carrying the previous rolling sum, and if we run into a count, we add that count to the rolling sum, and we keep going. So it's going to be, I'm just going to show the animation one more time. So that's how you compute that. And as for some
that final count should be equal to the size of the array, correct?
The final count should be the size of, yes, that is correct. That's a good point that you make, because if you look carefully at this count, we start at 1. So this is a 1 indexed array. So if we're thinking about how this relates to position in an array, if you were to subtract 1 from all of these elements right here, that would tell you like explicitly position in an array. So an array of size 7, the ending of the rolling sum, yes, will be 7. That is correct. And as another step, you're going to see there's going to be a -1 in there. So where we actually convert the 1 indexing to a 0 indexing so that we can translate basically 7 referencing array bracket 6, if that makes sense. But good point. Yeah, I think you're a little bit ahead. So once we perform the rolling sum, the intuition here is basically like guaranteeing where you will see a character potentially, right? So we counted 1, 0, right? And knowing that, like, we define this range, knowing that 0 is the lowest element of the range. If we have 1, 0, then we're never going to sort a 1 anywhere before that 0, right? So that's why we have to do a rolling sum, right? So for instance, for a 2, anything past a 2 will have to be past 3, because we know before we start putting elements that are greater than 2, like before we start putting 3s, 4s, 5s, 6s in our array, we have to make space for this 1, and we have to make space for the 2 2s, right? So anything past 2 can start past the 3rd element of the array, and then so on and so forth, right? Because I mean, I don't know if my words are doing it justice. Y'all just see in the example. So the 3rd step, oh man, I keep doing this, terrible. So the 3rd step in this process is to see how this. Okay, so the 3rd step in this process is to make your 2nd auxiliary array. So as y'all can see, this is the 2nd auxiliary array that takes up, space that you need to be working with. And this one will be 0 indexed, starting at 0 and then ending at the number of elements in the previous array -1, right? So now this is going to be where you put your solution. So essentially what you do is you match the elements in your array to this count index, and that will tell you where to put it in this array. So for 8, if we're looking at 8 from the original array, we go to 8 in our auxiliary array, and then we look at the location, which is 7. 7 - 1 gives us this index, and we put 8 here. For 2, we go to 2 in our index array. See, 2 starts at position 3, so we put 2 at position 3. I mean, it would be 2 at position 3 and then 3 minus 1 to go from 1 index to 0 index, and we put it here. So it's third. For 3, we look at 3. 3 in the index array has position 4. The 4th element in this array would be here, so we put the 3 here, and so on and so forth. Specifically, once we have accessed the index array, we need to de-increment the index array, right? So if we put a 2 at 3, the next 2 will go in front of it, and so on and so forth. And let's see. And for the sake of this example, instead of iterating normally, like forwards through the original array, this example iterates backwards through the original array. And again, sorry to dump so much information on you all at once, but the reason that you would iterate it backwards through the previous array is that the sort is still stable. So I don't know if y'all have talked about stability in a sorting algorithm. Stability just basically means that elements that have the same value that are in a certain order, that order will be preserved after the sort is finished, right? So imagine you have 5 2s that exist in a previous array. They're going to be in the same order that they were in the input array, in the sorted array, and that makes it stable. So the only way that counting sort is stable is actually if you iterate backwards, which kind of makes sense if you think about it, because the last 8 that you see is going to be here, or a better example is 2, right? So the first 2 that you run into, you put it here, and then you de-increment the count index, and then the next 2 that you run into, you actually put it further ahead, which will just keep all of the instances that have the same value sorted in the same order that you found them. So that's the reason you go backwards, is to keep it stable. So that's just a little fun fact right there. And then there's an animation here. So you de-increment this index array, move 8 to where it needs to go. For 5, you look at the index array, you're going to de-increment this 5 to a 4, and move 5 where it needs to go. Okay, so any questions?
I wanted to ask, like, why is stability important?
That's a good question. From a high level, stability might be important if you are performing a search on an attribute of an object. So, like imagine you want to you have like a system that's processing customers, and you've got like a customer object that has like, I don't know, maybe a feature of like how much money they're trying to spend, and you want to rank the customers, like the ones that are spending the most money, you want to, you know, serve their order first. But customers who are spending the identical amount of money, you want to serve them in the order that they showed up. So that's an instance in which preserving, I mean, that's kind of like a specific example, but that's an example in which preserving the order of equal elements might be important, right? So in this array, we're kind of given these abstract integers like 8, 2, 3, 0, 2, 5, 8. So you might think, why does it make a difference if we put a 2 here or a 2 there? But we might be dealing with attributes of an object. So this 2 might actually just represent some value in an object that has other data inside of it. So that's a good question. And I think it'll come up later. There are like algorithms that y'all learn about that are derivative, like they build on other algorithms. And some that y'all are going to see later in the class only work when a sort is stable, including the next one that I'm about to show y'all called Radix Sort, which only works with stable sorting. And I'll kind of explain when we get there, but that's a good question. That's a really good question. So let's see. I'm gonna go to VS Code. Like always, just, you know, waving my hands and telling y'all, take my word for it. The code does this. It's just, I'm not satisfied with that ever. So I actually did code up the counting sort. So I'm gonna run through an example of what that looks like in code. So as you can see in this function, I've defined an array printing function. So you take a pointer to an array and the size of the array, prints out the array, super standard stuff. In this main function, we've got 2 examples. So in the first example, we're sorting a relatively smaller array. This is actually the exact one that just came from the slide that I was looking at. Yeah. See. Yes, this is this exact example 8230258 should be exactly 8230258. I'm gonna go ahead and comment out this example so that we're just running one at a time. And then let's actually look at what's happening in the counting sort function. So in the counting sort function, the first thing that you do is you make your auxiliary space. So in this case, we're sorting digits. I don't know if you noticed, but we've got an array that is, I called it a digit. There's no nines. So technically we only need to represent from 0 to 8. But just for consistency's sake, I say we need space to be able to count each type of digit, which in this case is 0 through 9, which is 10 types. The first step is to count the discrete values. So you basically iterate through your input array, and then in your auxiliary array, you increment whatever you find, right? So if array of I equals to 8, right? And then the 8th index of count plus equals 1, right? So eventually, and I'll print this out, you'll be able to see what that looks like. Next, you perform a running sum. So I've got a helper variable right here called last. And essentially, last only increases, never decreases. That's how you get it to stay monotonic. And at each element, you add whatever's in the counting array to that last, and then you update this variable, and that performs a running sum. I'm going to print that out also. You'll be able to see. I shift from 1 index to 0 index to just get it over with. You know, it makes sense. So you just iterate through the count array, minus equals 1. You'll be able to see that too. And then this is the most complicated step. So this right here is your second auxiliary. I should label that. This is your second auxiliary array. This is the one that is going to contain your solution. So second auxiliary. Man, did I spell that right? Auxiliary. Definitely not. Whatever. And then once you've declared your second auxiliary array, you match values to locations. So this nasty statement right here, I can kind of give you some intuition. So essentially what this is doing is array of I is gonna respond to your input. So maybe you're looking at array of I. If it's the first element, it's gonna be 8, right? So array of I is 8. And then you're referencing where that exists in the count array. So this will give you the index of where it needs to be in the sorted array. And then you actually call that for the sorted array, and then you put your element there. And then you have to handle moving the count down by 1 each time. And then I print out the sorted array. So go ahead and run this. So and I called it count CPP. Okay, cool. Okay, so you can see the output. Let's compare this to what happens in the code. So the first thing is you count the discrete variables. So the array before counting sort is what it looked like in the example. And then we count the values. So you can see these correspond. We've got 1, 0. We've got 2 2s, 1 3, 1 5, and 1 8. It goes all the way to 9 in my example, but we don't have 9, so that'll just be a 0. And then you perform the running sum. So 1 1 3 4 4 5 5 5 7 7. Again, I explained how that worked. And then you switch from from 1 indexing to 0 by decreasing this by 1. And then you got your sorted array. Yeah, that's what counting sort looks like. I'm going to go ahead and uncomment this bigger example just to prove that this will scale to a bigger input. Oh, oops, my bad. So this one is going to look like, this is a much longer array, and you count the values, and it's still the same principle, right? Like it doesn't matter the size of your input. You're just going to be having auxiliary space for the number of possible values. So even though there's 21 digits in this input, there's 10 possible values. So there's 2 zeros, 5 ones, 1 2, so on and so forth. You perform a running sum. You change from 1 index to 0 index, and then this is what it looks like when it's sorted. So this is O of N. So super efficient algorithm, cool one to look at. I still have yet to release a GitHub or anything, but hopefully y'all will be able to look at this at some point. So that's counting sort. Any questions, by the way? No? Okay. I've kind of beat this one to death. So let's move on. Radix sort. So Radix sort is it uses counting sort to implement it. It's kind of like the next level. It's a way that you can overcome the issue in which space complexity becomes out of control, right? So for counting sort, if you wanted to use counting sort on digits like 0 to 1,000, you would have to have space to count how many numbers are 645, how many numbers are 777, so on and so forth. Radix sort basically jumps over that hurdle by performing counting sort on each digit. And you're going to see this is why stability is an issue, right? So let's sort these values. Okay. So the first step is you sort all of the elements by the ones place. We just did this. We just sorted elements that are 1 digit. So assuming that this, like the tens place and the 100s place of these elements don't affect them at all, we're going to sort them only by the last digit. So I think it was Amsal's question, why would you care about preserving the stability of elements in an array? Like, aren't they all just the same? Well, my example was, what if you had an object that had extra attributes that are, you know, not explicit to the actual sorting itself, right? So for instance, this would be like an object that has a value for the hundreds place, a value for the tens place, and a value for the ones place. The whatever is happening in these other values is important information that doesn't help you decide how to sort them. And you're going to see why stability is important in a second. So basically, perform counting sort, but you're only looking at the ones place. So assume the code that I just showed you for counting sort, we run it, but only on the ones place. And then now the trick is we do that for each decimal place. So after we've sorted as you can see, the ones places are now all sorted. So this is 0, 0, 2, 2, 3, 3, 3, 3, 5, 6, 9. Now we're going to do it with the tens place. As you can see, we just rinse and repeat. And then now the tens place is all sorted. So you got 0, 0, 0, 1, 1, 3, 5, 6, 7, 9. And then lastly, we're going to do it with the hundreds place. And then boom, 0, 0, 0, 0, 0, 0, 0, 1, 3, 5. And if you notice, even though the ones place is now out of order, 9, 2, 5, 6, and the tens place is out of order, we ultimately end up with a sorted array. And this only works when it's stable, right? So essentially the intuition here is that elements that have the same hundreds place, if we're only looking at like these elements that have the same hundreds place, it's important that the counting sort was stable, because when we were sorting based on their tens place, we like if you look at all of the elements that have the same hundreds place, the stability is, you know, important for this number, which is also sorted if you look. So within the elements that are all sorted and have 0 as the hundreds place, 0, 1, 3, 5, 6, 7, 9, they're sorted by the tens place. Or hypothetically, if you were to have like an element in here that had the same 100s and the same tens place, those would then be sorted by the ones place. And what do you know? That ends up sorting the numbers. This is a really cool trick. I think that's all on this slide. When would be like an application of radix sort is another good question. Specifically, radix sort only works when you have like large numbers that you need to sort. Like not large floating point numbers, but large discrete numbers like integers that you need to sort very quickly. Heads up, so if y'all are taking an exam for this class and you see a question like, Jane has to sort 1 million social security numbers, what algorithm should she choose? It's this one. It's this one. Because radix sort is linear, it's space efficient, and it scales really well. So it took us 3 iterations to sort all of these numbers because we have 3 decimal places. But if we went up to 1 billion iterations, now we're just performing it 9 times instead of 3 times, you know. So it's it scales very well. Hypothetically, if you had a social security number that was what, 9 digits, you just perform this 9 times, and then by the end they would all be sorted. Yeah, so that's Radix Sort. Any questions? Okay, well, I assume y'all mostly get the point. I didn't actually code this. Maybe I'll have it for the next time. We'll see. And the last topic that I want to cover today, I'm just briefly going to do a speed run of the debugger, in case you didn't see it in the lab, because I know some of the TAs are, you know, a little bit shy when it comes to using the debugger, and that's fine. But I think it's super important, so I'm going to show y'all. If you look under week 3, there's an activity that's called the debug activity. And I'm going to open this in an integrated terminal, and essentially it's just like, if we actually dig through what these files are, it's like a program that you're supposed to input a UIN. So that'll be these. So you input a UIN and a mode, and then based on that mode, it gives you a different debugging activity. So don't get too caught up on what's actually happening there. So see, I'm in an integrated terminal here. Let's see. I'm going to go ahead and compile. So and then what's this main CPP? Okay, so now that we've got an executable, we can debug this program. To debug a program, you have to attach the debugger to an existing executable. So if you can't compile, you can't debug. But essentially, once you've made it past the compiler, and now you're in runtime level, or so that's, seg faults, aborts, traps, whatever it may be, you can attach the debugger to the executable by specifying the name of your debugger. For Windows is GDB, for Mac it's LLDB, and then the name of the executable, which in my case is a.out. As you can see, now we're in this window, LLDB opens up and we can run. Normally you would type run, but if you have to run with command line arguments, which I do here, you'd have to specify these. So don't worry about these numbers. These are just specific to this program. So yes, permission. So as you can see, this option, like this assignment, this debugging activity was specifically compiled, like it was composed, it was written so that there are seg faults in this program that you can identify. And when you specify these parameters to the program, it does reach a seg fault, which in this case is specifically a signal abort. And as you can see, we can see the stack frame where the seg fault happened. But now you might be wondering, okay, well, why do I care that I have this hexadecimal address? This is where your program was. Like forensically, you can go back and identify. This is all of the function calls that led to the seg fault happening. And as you can see, this doesn't actually correspond to the line numbers in your code because I didn't compile with the -g flag. So I'm going to go ahead and quit the debugger. Yes, and I'm going to recompile. When you specify the -g flag in this compile line argument, now your executable is going to be tracking the line numbers so that in case it does crash, it will be able to recover the information about the stack frame. So I'm going to type in just what I had typed in before, but now that we've compiled with the -g flag, go ahead and backtrace. Okay, now you can see these are the actual lines in our program where the seg fault, like this is where our program was that led up to the seg fault, if that makes sense. So as you can see, the first function that we were in was main, and then from main, we entered this function, which entered this function, which entered this function. And essentially this program was designed to be confusing, so you don't know what's happening anymore. But if you wanted to, you could track it down. So base types.age45, see what that looks like, 45. And as you can see, it's throwing an exception. So, that's a little fun thing you can do. I'm going to go ahead and run, oops.
Can you track the call stack?
The call stack?
Yeah.
This is that. So like, for instance, we started at main line 106, which, let's see, main line 106. So we started here, and then we entered the switch where we entered this mode 1 UIN. So this took us to mode handlers.h28. So mode handlers.h28. So that took us to this function, which took us to mode 10b obfuscation. I mean, I guess mode 1 obfuscation. Sorry. Anyways, which you can see took us to obfuscation.h line 18. And then these represent the line number and the column that the error happened on. I mean, or the call stack was on. Specifically, it's column 2124. This nonsense. Look at this nonsense. This is complete crap. But yeah, so this is, see, column 1600. We're looking for 21, 24. So it's one of those functions which took you somewhere else. So 1823. What if you like throw on some line, probably base.types 45. And then yeah, throw another error. So essentially that's the debugger. And maybe the next time I'll go over through like how you would actually do some advanced stuff here. But basically all I did today was you run the program, you type BT stands for backtrace, and that'll show you the stack frame. So good question. We are out of time. I want to respect y'all's time. It is the weekend. So if y'all have like any specific questions, I'd be happy to answer them now. As far as like material that I was planning on covering, that's pretty much it. So any questions?
All right, so I got a question now. So the file, the link to the big O file, it said that it is access denied. So can you open it?
For the big O file?
Yeah.
So y'all can see my screen, right?
Yeah, I can see your screen.
Actually, no, I probably shouldn't do this. It would totally be a FERPA violation. Actually, whatever. Okay.
Yeah, but I mean, when I click to the link you put on the chat, it said access denied. So
Yeah,
I
so
think that,
you go to the way that you can find it is if you go to Canvas, you go to modules, then module 3, and then
all
I
right.
think,
Oh yeah, if I can find it, so it's good.
yeah, you can just find it. So you go to week 3, and then you click on week 3 topics, and then Big O practice will be at the bottom.
Okay, I got it. Thank you, man.
Yeah, cool.
All right.
Any other questions? Okay, well, thank you all for being patient. I respect the grind as always. If you're here on the weekend, you're going to do well in this class. It's good to see y'all showing up. Y'all are free to go. Yes, thank you.